Hello, everyone, and welcome to another Math and High Energy Physics seminar in Physics Latam. Today, we're honored to have Professor Sven Heinemeyer, a leading researcher in theoretical high energy physics. He obtained his PhD in theoretical physics at the University of Karlsruhe in 1998 in Germany. His work focuses on physics beyond the standard model, supersymmetry, and Higgs boson phenomenology. Over the years, he has held research positions at DESY, Brookhaven, CERN, and the University of Zaragoza before joining the IFT-Madrid as a senior researcher. Professor Heinemeyer has made significant contributions to the phenomenology of Higgs boson at colliders, serving as a leader in multiple Higgs working groups at the LHC and helped to develop widely used theoretical tools like Fein Higgs, Higgs bound, and Higgs signals. And well, his research also explored the interplay between dark matter and supersymmetry, as well as precision tests of the standard model and the minimal supersymmetric standard model at current and future colliders. Thank you so much for accepting our invitation, Professor.
Thanks a lot for inviting me. It's a pleasure to give this lecture. The overview about the transparencies I've prepared, you can see here. We will have some basic stuff on the standard model to set the basis for everybody. Then I will say something about Higgs physics at the LHC in general, explain certain concrete realizations of BSM Higgs sectors, and then tell what if one looks at those and tries to see what can be done at the LHC. This is a huge topic. Yeah, many things can be said, and therefore I write here selected. I will focus on an aspect that is the current focus not only of my research but also of the Higgs working groups of Atlas and CMS at the LHC, and it's a topic that became more and more relevant over the last years, and I decided to put the focus on here. And if time permits, in the very end, I will tell you about my favorite LHC Higgs anomaly, which may or may not be true. We will see. Good. Let's get started. The Higgs in the standard model. Why do we need a Higgs at all? And the reason is relatively simple, as I will explain to you in a moment here. I start here with quantum electrodynamics as an example. And we have here the photon that transmits the force between charged particles, in this example here, electron and a charged nucleus. And the Lagrangian can be seen here. The fermion, the electron, is given by this psi here. And the a mu, the photon, is part of this covariant derivative that we can see here, which is all caused by the construction requiring the invariance under the gauge symmetry, the U1 in this case. I will not go into more details here. Important thing is that the photon is here inside the mu, and this is the kinetic part for the photon. And one requires that the Lagrangian is invariant under the local U1 gauge symmetry, and I've written down here the gauge transformations. Everything works out. The Lagrangian that I've shown to you is fine. However, once you decide, well, I want a massive photon, so you notice here this is only a toy example because we know in our real world the photon is massless, but if one wants to describe a massive gauge boson, then one can just insert a massive mass term into the Lagrangian. However, one sees then that the Lagrangian is not gauge invariant anymore. Applying here this equation 2, one gets these additional terms, and as I said, the mass term violates the gauge invariance. Conclusion: gauge boson must be massless. No problem, as I said, with the real photon, it is massless, but we will see in a moment where the problem arises. This is the picture of the particle content of the standard model. I write here as of the year 2011, and we can see here the quarks, the leptons, and the force carriers, the gauge bosons, with the 3 families, first, second, and third family. And here we have the gluon, the photon, the gluon, and the Z, and the W. And I write here as of 2011 because one particle is missing that I will add in a moment. And as I was telling you before, the construction principle requires that all these gauge bosons are massless. However, well, sorry, I should say this here. However, the problem is that we know experimentally that the Z boson and the W boson are highly massive. The Z boson has a mass of around 91 GeV and the W boson of around 80 GeV, so clearly not massless. And people thought for a long time how one can construct consistently a theory that incorporates masses for the gauge bosons. And the idea that was thought up is now called the Higgs mechanism, or sometimes also the Brout-Englert Higgs mechanism. And I will again show this to you in a toy example, come then to the standard model, and then I will use this as a basis to go beyond the standard model. But this is only the toy example here. We introduce the complex scalar field phi that has a vacuum expectation value. I'll tell you in a moment what this means, which is constant in time. And the Lagrangian of the new Higgs field is then simply given by the kinetic part and the potential. The kinetic part is shown here, the covariant derivative applied to phi squared, and then the potential contains a quadratic and a quartic piece. Now, how can or should we choose these two parameters that we have here in the potential, the mu squared and the lambda? And lambda, this is very simple, has to be chosen positive so that the potential is bounded from below. Now I see that somebody wrote something in the chat because this line popped up. So you just, Esteban, you take care of that, yeah?
Yeah.
I will, whoops. Just, the problem is that this always takes away the upper line from my transparencies here. Okay. But you take care of the question, yeah? As I said, lambda has to be chosen positive so that the potential is bounded from below for large values in field space. But mu can be chosen positive or negative, and one can choose it effectively by hand. And as we will see in a moment, if one chooses mu squared negative, this yields the required vacuum expectation value. And I'll show to you how this works out. This complex scalar field can be parameterized by two real scalar fields, which are called also the small phi and the eta. It's given here by the absolute value and the modulus. And if one inserts this into the potential, one finds that one gets simply mu squared phi squared plus lambda phi to the fourth. Now we want to minimize the potential. Where is the minimum? Because we know that we certainly live at the minimum of the potential, yeah, the lowest energy state. So we take the derivative and we set it to 0 to find the extremal point. And then if mu squared is positive, one finds a very normal, let's say one finds this kind of shape and we live at the minimum. But if mu squared is negative, one finds that the minimum is shifted away from the origin. And given by this value, the square root of minus mu squared over lambda, which is then our so-called vacuum expectation value. So the distance in field space from the origin to where we live, the minimum of the potential. And I'll show you a graphic in a moment to how this looks like. So we have here this potential. And as I said, mu squared equal to positive gives us this form here, which doesn't help us. But as you will see in a moment, if we select mu squared negative, we get that the minimum is away from the origin here. This is the vacuum expectation value, this distance here, when then we live in the minimum of the potential. Sometimes there's a square root of 2, sometimes not. This is just a convention. And I'm afraid that I'm also not entirely consistent, but it doesn't matter, yeah, whether you have the square root of 2 or not. This doesn't change any of the physics. Good. So this is what we want. And why do we want this? Well, I'll show you why we want this. First of all, we pick a special phase, a so-called gauge, called unitary gauge. We set the alpha that transforms, which comes from our gauge operation here. We set it to this minus eta, which was contained in the complex Higgs field. And if one does this, one effectively gets rid of the complex part, and the covariant derivative times applied to phi squared is then reduced to the normal derivative on phi squared, so normal kinetic term. plus a second term that is now quadratic in the a mu and quadratic in the phi with this prefactor here. Yeah, so we have here Higgs field squared times a mu squared. Good. Now one can expand this phi around the minimum. Yeah, one says phi has a constant value plus then what we call the Higgs boson. This is the remaining degree of freedom that is still in our game here, which can be interpreted, as we'll see in a moment, as a real scalar boson, which we now call the Higgs boson. Yeah, we can, as I said, the expansion around the minimum. And if one does this, one sees that the Lagrangian of the Higgs now contains one piece that goes like mh squared Higgs squared, so the mass term that we need, where the mass is given by this combination, 2 times lambda, the mass squared is 2 times lambda times v squared. And then we have a triple coupling and a quartic coupling given by these values here. Good. But the important part is what happens with the photon. I write here inserting this into that. I guess that in the end, I'll send you a copy of the PDF, and then you can go step by step if you're interested to see how this works. If one carries out all these insertions, one finds that the term that connects the Higgs and the photon that comes from the coupling of the Higgs field with the gauge boson field gives us a mass term, ma squared times a mu squared, where ma squared is given by v squared times e squared q squared that we introduced before. This is now the mass of the photon. Then we have a piece that is given, well, a trilinear coupling between the Higgs and the photon, 2 times the photon. And here we have a coupling between 2 times the Higgs and 2 times the photon. And one can see that these prefactors, they only differ by the powers of v. But in principle, they're all proportional to each other, which is a crucial prediction, which is also extremely important for Higgs physics at the LHC, as we will see later on. Okay, I said the second term is the Higgs photon-photon interaction. The third term is the Higgs-Higgs photon-photon interaction. And the fact that I try to stress here, that the mass squared here is proportional, has the same prefactor as the triple and the quartic coupling. This is the decisive prediction of the Higgs mechanism. Yeah, the coupling of the photon to the Higgs is proportional to its own mass squared. Yeah, so when we know the mass of a particle, we know already what the Higgs sector predicts about its coupling to the Higgs itself. And what we do at the LHC, or a large part of the physics now done at the LHC, is trying to probe this relation, or try to find deviations from this relation in order to find deviations from the standard model. Yeah? So this is the characteristic prediction of the Higgs mechanism. And also for fermions, one can do it in a similar way. One can write down, well, here, this is the representation for the fermions, the chiral fermion. We decompose into the left and right-handed part. We can write down the Lagrangian. Here we pick one prefactor, which is called the Yukawa coupling. Then we have the psi L dagger, phi psi r, and inserting again these the VEF plus the Higgs field, so the evolution around the minimum. Then one finds these two terms. First, a mass term, m phi psi L dagger psi r, where the mass is given by this prefactor y psi times again the VEF here and square root of 2. And here we have a coupling of the Higgs to fermions. Again, the coupling is proportional to the mass of the fermion. Yeah? By construction, the coupling of the fermion to the Higgs boson is proportional to its own mass m psi here. Again, this is the characteristic prediction of the Higgs sector, of the Higgs mechanism. This is an alternative way to see it, but maybe I'll skip it for sake of time. Let's see how this works out in the standard model concretely. And I said, this is very short. And once we know how it works in the standard model, we can go beyond the standard model and see what modifications come into place here. In the standard model, We have in the electroweak part, we have not only the U1 symmetry, but also the SU2 left symmetry. And in total, we have not one gauge boson, but we have 4 gauge bosons, the B mu and the W mu A, where A runs from 1 to 3. This here is again the kinetic part for the two, for the gauge bosons, for the B mesons, B bosons, and for the W bosons. And here is the kinetic part, and we have the Higgs potential. Higgs potential looks as it looked before, but this is crucial now. The phi is not just a scalar, it's a scalar, it's a complex doublet. Before we just had a complex singlet, so to say, but here we have a complex doublet with a neutral and a charged component. And this means that we here start out with 4 degrees of freedom. This is very important. We add, by the introduction of the Higgs field, we add 4 degrees of freedom to the model. Now, the covariant derivative contains, as it did in the toy example here, the W bosons and the B boson with their respective couplings. As I said, these are the kinetic terms. We have the couplings of the SU2L and the U1, the G and G prime, Pauli matrices, structure constants, and so on. I will not go into details. In principle, this looks as in the toy example, but with the difference that now phi is a complex doublet. And again, we can choose a minimum away from 0. If mu squared is smaller than 0, again, we call this V, and then the structure of the Higgs field looks like this. In the upper component, we have a 0, like we got rid of the other. Well, this is just a vacuum. This is just a vacuum. In the vacuum, we just have here 0 in the charged component and V in the neutral component. And V is given as before, s squared of minus mu squared over lambda. Now, the original field phi can be expressed through the vacuum expectation value, the Higgs boson, and 3 so-called Goldstone bosons, the other 3 degrees of freedom, phi 1, 2, 3. And the question is, why do we want 3 here? Yeah, this may look arbitrary, and I encourage you to think for one moment why we want 3 Goldstone bosons here. But if you remember the listing of the particles in the standard model, we had the massless bosons, the gluon, which doesn't enter in this game at all because we look only at the electroweak part. We have the massless photon, we have the Z, and we have the W. But the W, actually, these are 2 particles. It's the W plus and the W minus. So we have to give masses to 3 gauge bosons. The Z0, W plus, W minus. And this is where we need these 3 extra degrees of freedom, the neutral one and the 2 charged ones. Then one can work everything out, and the W's that we know, the W plus and the W minus, are given by the first and the second component of the W triplet added in this way. And the Z and the photon, they are actually a mixture of this third component of the W and the B mu field. This CW or SW is the sine or the cosine of the weak mixing angle, which is given by the 2 gauge couplings. So if one writes down the Lagrangian, one sees that the mass matrix of the W mu 3 and the B mu is not diagonal. One has to diagonalize it. One does it via this mixing matrix, cosine minus sine, sine cosine, which rotates one set of states into the other set of states. Yeah? And we arrive at the Z and the photon. And nicely, it turns out in this construction that the photon, if by the diagonalization of the mass matrix, receives the eigenvalue 0, so the photon remains massless, whereas the Z receives its mass from this diagonalization, the Z boson mass. And if one writes on the Lagrangian later on, one finds then exactly what I was saying, mw squared W plus W minus plus 1 over 2 mz squared z squared. And then the Higgs field appears as it did in the toy example before, 1 plus h over v squared. It's exactly as before. And then we have the Higgs potential here. These are the expressions for the gauge boson masses. This is then the mass of the Higgs boson within the standard model given by this expression here. This is all, this all works out. And since here we have the gauge coupling and the VEF, and we know the masses of the W and the Z, we can actually calculate the value of this vacuum expectation value within the standard model, and it's around 246 GeV, the generic electric mass scale. Yeah, and this mixing angle, the cosine, is given by the ratio of these two masses here. And also for the fermions, it works out exactly as before, but there's one little trick that I have to mention. One starts out here with the doublet, top left, bottom left, the SU2 doublet of the left-handed parts. The SU2 is a left-handed, so it's SU2 left, so it applies on the left-handed parts of the fermions here. We start out with a doublet, and if we have this construction here, QL, dagger, phi, and then we write the right-handed component of the quarks, BR, one sees if the phi has this structure here, 0 and then V plus H, it will only give us a non-zero value for the BL. So this piece here can give us a mass term for the bottom quark, but not for the top quark. Well, for the bottom quark works out. What do you do for the top quark? We play a little trick. We apply the second Pauli matrix with an extra factor of I to the complex conjugated field phi, which is then called phi sub c. And this simply moves everything upstairs. And then this construction multiplied here multiplies the TL, and we get the mass term for the fermions as well. And then we get this kind of term, bottom quark mass B bar B, 1 plus V over H, and the same for the top. And as I was saying before, one finds exactly again by construction that the mass, that the coupling of the Higgs to the fermions is proportional to the mass of the fermions. So in the standard model works exactly as in the toy example. Good. Finally, the Higgs boson mass itself, which is given by this kind of diagram here, where the Higgs couples twice to its own VEF, and we know that the quartic coupling is given by this lambda, and then one can work everything out and finds that this is V square root of lambda. Very good. And this is or was for many, many years, for decades, the last unknown parameter in the standard model. Now, of course, it has been measured. And this is the crucial sentence that you should take home from this part of the lecture: to establish the Higgs mechanism. So this is what we want to, what we are doing now at the LHC. To establish the Higgs mechanism not only means finding the Higgs, but in particular measure its couplings. Yeah, this is the crucial part. And here again, I encourage you to think for a moment for about two things. First, how can one measure Higgs boson couplings? How could one do this? And what else might have to be measured or tested at the LHC? Yeah. If anybody wants to say something, I encourage you to do it now. There are no stupid answers. I know that it's very difficult to click on the button and get the courage to say something, but I can only encourage you to do so. Yeah. Also, if you have any questions on this part here, you can also ask them. But think for a moment, how, if you are now a physicist and you have here this theory, how can we measure the couplings of the Higgs boson? Yeah. Well,
you can unmute yourself if you want.
Yes, yes. It's always difficult to wait for some time or so, but I hope that people are at least thinking about it now, even if they don't dare to say anything, but I hope that they are thinking about it. The answer is quite simple. If one hears the answer, it's quite simple. Well, we have to measure the probability with which the Higgs boson decays to a certain particle. Yeah, because the probability is directly related to the coupling, to the strength of the decay of the Higgs boson, which is then given, or should be given, according to the standard model Higgs mechanism, by the mass of the particle itself. We'll come back to this in a moment. And what else should be measured? Well, for example, the theory predicts that it's a scalar boson, a spin zero boson. So we should try to measure the spin. Yeah, this is one characteristic. There are many other things, but the very simple characteristic that one should test, and that is tested, I will not go into details, is whether it's a spin zero boson. And so far, all indications that we have tell us, yes, it is a spin zero boson. There can be small deviations, but overall, this is what one finds in the current experimental data. Good. Now that you've thought about this, let's move on. This is one more thing that I like to show before finishing with this part. There was a reason, and this is also related to current ongoing LHC experiments. There was a reason already before the Higgs discovery that told people, yeah, there should be something like a Higgs boson. And the reason is the following. It's more like what we, in the nice German word, Gedankenexperiment. Yeah, so you just think about a possible question here. And the experiment that we think about is the scattering of two double bosons going to two double bosons. Yeah, we can't, it's very difficult to realize this experimentally at the LHC. They try to do this now, but this was done long before the LHC went into operation. And then you calculate the amplitude of this process. WW goes to WW. And the diagrams that are contributing in the theory without a Higgs is here the photon or the Z exchange, also here in the T channel, the photon and the Z exchange, plus a quartic coupling. And then you evaluate this matrix element, and you find that for large energies of the incoming W bosons, this goes like coupling constant squared times energy squared over the W boson mass squared. So, and this is extremely dangerous. If you haven't seen this before, if you haven't thought about it before, why should this be dangerous? Yeah, well, why? I mean, you get this out, fine, you can calculate the cross-section, everything is good. Why is this dangerous? Well, it is dangerous because the cross-section that you can calculate is also a probability that this process, WW goes to WW, happens. And we all know probabilities are bounded from above by 1. But if a probability grows to infinity, the theory is ill-defined. Something goes wrong. This theory cannot be correct. It violates, as we say, unitarity. And then people thought, what can we do? And they found that by introducing a scalar particle into the model, and I called it already H here, which has then two diagrams, this S channel exchange or the T channel exchange here. This also gives you an amplitude that grows with the energy squared with a coupling constant here of this H particle to the gauge bosons. And remarkably, the sign is different. Here we have a minus sign and here we have a plus sign. So we sum up everything, and then this dangerous term has this prefactor, which of course can be made 0 if we require this relationship between the couplets. And this is exactly what the Higgs sector or the Higgs mechanism predicts anyway. So the Higgs mechanism also cures this problem automatically. And one can see this nicely in this plot that I stole from a friend of mine. It's Englert. He's a professor in Glasgow, a theoretical German theoretical professor for theoretical physics, not related to Englert, to the Nobel Prize winner. But he did this plot, therefore I cite him here. And this is the cross-section for this process as a function of the center of mass energy, so the incoming energy. And if one only has a photon here in the exchange, then we find this, that it grows to absurdly high values. The theory becomes invalid very, very quickly. if one looks at all the exchange here with the Z and the quadricoupling, it behaves already better, but still at some point it doesn't. Only if you include the Higgs boson, then you find this behavior that is okay. So this was another reason why we should have a Higgs boson in the game. Good. So now that I've convinced you that we need the Higgs, that there is a Higgs, let's come to first a bit of standard model Higgs physics at the LHC, and then we go beyond these physics at the LHC. Good. Just to set the basis, the LHC is a ring where protons collide with protons at a center of mass energy designed to go up to 14 TeV. This is an aerial view of the region there close to Geneva. One always points out this is Geneva Airport. This ring has 27 kilometers circumference. Of course, the ring is something like 100 meters underground, as we will see in a moment. So it's not visible from the top. But yeah, this is where it's located. Here below, there is CERN located. And in this P1, this is where the first big experiment that's relevant for us, Atlas, is located, whereas CMS is here at P5. So if you belong to the Atlas collaboration, you leave CERN, you cross the street, you're at your experiment, everything is fine. If you belong to CMS, you have to drive half an hour through the countryside to arrive to your experiments there. There are two more experiments which will not concern us today, LHCb and Alice, and several smaller ones, but the big important ones are Atlas and CMS. And maybe I skip this, I just show this one here. Now here we look from the other direction. This is Atlas, this is CMS, it's at around roughly 100 meters underground, where the protons are colliding with each other. CERN is located here. This crosses the border between Switzerland and France several times. Good. This is the timeline of the LHC, and probably many of these years have passed before you entered physics or even started studying physics. It started out in 2010. It started out even earlier, but after running for a week, there was an incident and LHC had to be stopped for 1.5 years for repairs. Now this is all under control. So then after restart, this was in March 2010, with new record energies that had never been achieved before. In 2010, a very small amount, when you see this femtobarn, this inverse femtobarn, this is always the luminosity, meaning a measure of the number of collisions that you have. You can directly translate this into each other. So this was a very small number of collisions in the first year, 0.05 inverse femtobarn at a center of mass energy 7 TeV. Then this improved already to 5 inverse femtobarn in 2011. So first physics results came out. And then in 2012, with 20 inverse femtobarn, here this was already at a slightly higher center of mass energy, 8 TeV, the Higgs boson discovery was announced. We'll come back to this in a moment. Then after some time, there are always shutdowns, repairs, improvements, etc. Then they had the run 2 with 14 inverse femtobarn per year, and now at 13 TeV, another shutdown. Now we are in the so-called run 3 with more than 15 inverse femtobarn per year, and now at a center of mass energy of 13.6 TeV actually. In 26, there will be another upgrade, and in the end, they will go to the so-called high luminosity LHC, which will likely run until the year 41, I think is the latest number, and collect between 3,000 and 4,000 inverse femtobarn per detector. This is always per detector, not the whole machine, but per detector, so Atlas and CMS individually. And what does this imply for you? This implies that you're living in a really exciting time. Yeah, we have some luminosity, we have some events that are analyzed, but many, many more events will be recorded in the future, and many, many physics can hide or can show up in all the data that we will have for sure, because this is all approved and we will have the data. And maybe if we come to the last part of the lecture, there's a good potential to see something very new here. Good. I have here one slide, another take-home message, the LHC executive summary. The standard model has been rediscovered completely. We knew the standard model, apart from the Higgs. No evidence for BSM physics yet, but of course, the groundbreaking discovery in the Higgs searches, the Higgs boson, a Higgs boson has been discovered. Yeah. So if you want to tell somebody what have people been doing at the LHC, I think these 3 lines sum it up completely. Good. Before we come to the BSM, I still give a small recap about some properties of the Higgs boson, because when we go to the BSM models, we always see them relative to the standard model. This is much easier to handle rather than to say, here we have this coupling strength or the other. It will always be given relative to the standard model prediction. Well, and the first part I have here is decay to fermions. So we produce a Higgs boson. I'll show you in a moment how they are produced, but let's assume we produce a Higgs boson, and then it decays relatively quickly. And it can decay, for example, to fermions, and this is the coupling strength. Yeah, so this is the coupling constant now expressed directly with the mass and the Fermi constant. It's just another way to parameterize it. And this fermion mass, of course, contains the VEF, etc., but it's not relevant. Let's keep the mass here to show that the coupling is proportional to the mass. And then one can calculate the so-called decay width, the kind of strength of the decay, not the probability, the strength of the decay of the Higgs going to this particular fermion. And one finds that here we have the Higgs mass in the numerator. And then we have here the Higgs boson, the fermion mass squared. So these the coupling enters into the amplitude. The amplitude is absolute squared with some prefactors to give you the decay width. Then we get here the fermion mass squared times this phase space factor and the factor that comes from the overall calculation. And one can see, of course, if this is only, you can only make sense if the Higgs is heavier than twice the fermion mass, so that the decay can kinematically actually happen. Yeah, this goes to 0 if the fermion mass approaches half of the Higgs boson mass. Good. One important thing, particularly for the quarks, one should evaluate these quark mass here at the scale of the Higgs boson mass. Yeah, and particularly, well, we will see where it's particularly important. This moves, as I said, this pole mass of the quark, which is not well defined anyway, to a better defined ms bar mass value at the Higgs boson mass scale, and this can give very large corrections up to a factor of 2 or so. So if one has this knowledge, one knows already what is the strongest or the most important decay of the Higgs boson at the LHC. Well, at any collider. If one looks at fermions, we come to the gauge bosons in a moment. What is the strongest decay? Well, we know that the top quark mass has the largest mass and therefore has the largest coupling to the Higgs. And then one could think, yeah, then it could decay to top quarks prominently. But as I was saying here, the Higgs boson mass must be heavier than twice the fermion mass. The top quark is at 173 GeV, and this is by itself is already larger than the Higgs mass, and twice the top mass is even much larger. So top doesn't work, meaning the most important decay here, the strongest decay, is decay to B quarks. This one here, and all the others are subleading. And if we look here at the B quark mass, this is the usual factor. This m bottom pole squared moved to m bottom squared at the Higgs boson mass give us a factor of 1/2. Yeah, so this is only half the size of this, meaning the decay width is only half of what we calculate naively. Yeah, therefore, these QCD corrections are very important. A decay to gauge bosons, to massive gauge bosons, there we have the coupling. The coupling is proportional to the mass squared. And then we can calculate again, if the gauge bosons are lighter than half of the Higgs boson mass, one finds these prefactors, Higgs boson mass cubed, and then here the gauge boson mass is enter, and again this phase space factor. However, I told you already, or you know probably, that this is not possible in the standard model. There is no on-shell decay of the Higgs boson to the gauge bosons, because the lighter of the two ones, the W boson, has a mass of around 80 GeV, and 2 times 80, 160, is larger than 125, and then this is not possible. But there are also off-shell decays where the gauge boson only appears virtually, and then this decay is actually possible, and one finds a different behavior that is then proportional to the mass of the gauge boson to the 4th power here. So this is what one finds. And we will see how important this is in a moment. Finally, decay to massless gauge bosons, to a pair of gluons or to a pair of photons. And then you may ask, hey, how is this possible? Just a moment, you told us that the coupling of the Higgs boson to a particle is proportional to a mass. So it doesn't couple to massless gauge bosons. Huh? And you're absolutely right, it does not. But still, these decays are possible, and we will see how important this is, what I will tell you in a moment. This is possible via loop corrections. Yeah, we mediate the decay of Higgs boson through a loop where the Higgs boson couples to a particle that has a mass, and then this particle must have color charge or electric charge, and then decay to 2 gluons or 2 photons. So what are the most important loops? Well, if you think about it, for the Higgs decay to 2 gluons, obviously the top quark is most important. Yeah, so here it doesn't matter that the top is heavier than, twice the top is heavier than the Higgs, because it's only a virtual top. It's a closed loop. There, this is allowed. And then but this coupling here is very large, and then the top decays, or the top loop goes to 2 gluons here with a strong coupling constant here. And for the decay to 2 photons, it's actually the W boson loop that plays the strongest role. We need, of course, an electrically charged particle here. And then this coupling here is the strongest with the decay to 2 photons. Yeah? One can calculate, again, the decay width of the Higgs to 2 gluons. Also here, QCD corrections are important. They are also huge. And for the decay to 2 photons, we first, this 7 here comes from the W boson loop, and then this ET, this is the charge of the top quark. Also here we can have a top loop, and this is the second largest contribution, and they have opposite sign. They have a destructive interference, and then this gives us the decay to the photons. Good. To finish this up here, I said we want to measure the couplings. And how do you do this? Well, first of all, we perform a sum over all the decay widths that we can calculate. So D is not D quark, D is decay product. Yeah? So we sum over all possibilities, these, and then we have here the decays to top quarks, which is 0, to bottom quarks, charm quarks, etc., to the leptons, to the gauge bosons. The star indicates that one of them should be off shell, as I was saying, to photons, etc. And then the crucial part is to calculate the so-called branching ratio. And the branching ratio is the original decay width divided by the total width. And this is actually the probability that the Higgs decays to this kind of particle. Yeah? And this is what can be measured to some extent at the LHC. Yeah, this kind of probability. So the branching ratio, by definition, these branching ratios all sum up to 1. Yeah, if you do this, calculate the branching ratio for all the decays, and then you add them up, you get exactly the same sum in the numerator as in the denominator, and they sum up to 1 as a probability should. So this works out. And secondly, well, to second I come in a moment. Then in preparation for the Higgs boson searches at the LHC, there is the LHC Higgs working group. Those days it was called, turn your head, LHC Higgs cross-section working group. Now it's the LHC Higgs working group. And prior to the discovery of the Higgs boson, we produced these kind of plots. We didn't know the mass, so we did it for all the possible mass. And then this here is the branching ratio. And for low masses, the decay to BB bar is dominant. And then for high masses, decay to WW is dominant, as one can see here. So this rises, these are these off-shell decays. And then here the W is fully on shell, and then the Z also comes, and this is TT bar. And then here we have all the others. The decay to gamma gamma is quite suppressed. It's at the level of 2 times 10 to the minus 3 is down here. And I have, yeah, this is the last plot I show here. This is zooming in already at the area that is interesting or important for the LHC. Said we know now that we are sitting here at 125. And if one could choose a mass to do interesting physics, one would choose probably exactly this mass. Because for lower masses, we see all the fermions nicely, but we can't measure the coupling to gauge bosons. It's not possible because here they're just too small. It doesn't work. If one has a high mass, the couplings to gauge bosons dominate, and we can't measure the decay or the couplings to quarks or other fermions, to the leptons. So something right in the middle is here where we have access to all the decay modes that we can imagine, except to TT bar. And we are very fortunate in this respect. Now, as I said, Higgs physics at the LHC. How do we produce a Higgs boson at the LHC? Before we can decay, it must be produced. And there are 5 important channels. And the most important one is actually this one here. We start out with 2 protons. Then from each proton, we take a gluon. Then they form a loop, a quark loop, like top loop. And then we get a Higgs out. This is the process that we've seen before for the decay, just reversed. Yeah, before we saw Higgs decays to 2 gluons, and here we take the 2 gluons to produce the Higgs boson. And this, actually, although it's a loop-induced process, is the most important production mode at the LHC because of the strong couplings that enter into the game here, and because of the large gluon content that we have at the LHC in the protons. The second most important one is the weak boson fusion. Here we start out with 2 quarks. They both radiate either a W or a Z, and then they give us here the Higgs boson, also very nice. The third one, we again started with 2 quarks. They go here in the S channel to a Z or a W, which can then radiate Higgs boson also. And finally, we can produce 2 top quarks, and the Higgs is radiated from a top quark. Well, these are the most important production modes, and they're summarized in this plot here. Again, as a function of the Higgs boson mass, this was done. This plot is from the year 2010, so long before the Higgs was discovered. We are roughly here, 125. One can see this is the glue mode, yeah, which is larger by 1 order of magnitude than the second one. This here is the weak boson fusion, the WW fusion mode, and then comes radiation from a W, radiation from a Z, and radiation from a top quark, which is the smallest one. Yeah, but these are the predictions. I didn't explain also not in the previous plot why we always have these colored bands. The central value, very difficult to see here, there's a black line, this is the central value of the prediction, and then this is the theory uncertainty, coming from the unknown higher order corrections. Yeah, we perform loop calculations, we improve, we calculate the quantum corrections, but never to infinite precision, and then this is what remains as an uncertainty. Good. And I think this is the final one that I have here. And I will show you some plots in this direction. What are the LHC observables? And this is not only important for the Higgs boson that we've seen there, they were all used, but also for the searches for BSM Higgs bosons. Yeah, they are ongoing searches. I will show you some results. And there also these quantities are used. And the first one is the so-called local p-value. The local p-value is the probability that the observed number of events is caused by background only. And in this case, when the Higgs boson was searched by the standard model without a Higgs boson. And I'll show you the plots in a moment. I skipped this one here, but the signal strength is also something very important, used all the time, which is we measure the Higgs boson in a certain production mode, and then in a certain decay mode, we take the product, and this is measured, observed at the LHC. and then we divide it by the standard model prediction. And if the standard model is correct, the value should be 1. Now, of course, we try to find deviations from 1. This is all ongoing, and we will see how this works out with BSM Higgs boson searches at the LHC as well. Now, this is a famous painting about the 4th of July when the Declaration of Independence was presented. But if you look very closely, you see that this doesn't look like the Declaration of Independence. These are actually, I will not show them in detail, but these were original plots produced for the Higgs discovery. Because I ask here why. The reason is that on the 4th of July 2012, Atlas and CMS presented their results to the public. So that, of course, looked into the data for quite some time. I said they started in 2010 and 2011, the real first data. There were some indications already by the December 2011, but at the level of 3 sigma or something like that. And then on the 4th of July 2012, they announced the discovery. And these are the original plots they showed there. This is this local P0 value as a function of the Higgs boson mass. And as I said, it's the probability that what you see could be caused by background only, meaning standard model with no Higgs. And if there is nothing, this should be around 0.5, 50%. And one can see here, Atlas is around this value, 0.5, fine also here. But then there's this sharp drop around 125 GeV, where the probability that what you see, the numbers of events that you see, could be caused by the standard model without a Higgs, drops to the level of 10 to the minus 9. Or correspondingly, it's a deviation from the hypothesis that there's nothing of 6 sigma. And this is then called a discovery. Everything above 5 sigma is called a discovery. And the great thing is that not only Atlas presented these results, but that CMS had a similar plot. Here, this black line, also it starts around 0.5 or so. The scale is different. Here we go from 110 to 150. This is only 115 to 130, but also here around 125, we see that this line drops and they go to the 10 to the minus 7, corresponding to 5 sigma. The fact that they are a bit more down and they're a bit higher, these are just fluctuations in the data, statistical fluctuations. But this is what has been discovered. But I show you here the discovery plots, but I show already BSM Higgs sectors, and this is the motivation. This alone is not a motivation, but I'll show you the motivation. It's coming, And well, this is the second part of what is presented, what has been measured. Not only we have discovery, we have what we call a standard model-like discovery. Now, these are measurements with much more data, partially run 2 data, Atlas, measuring the various production modes, gluon fusion, big boson fusion, radiation from a W, radiation from a Z, or radiation from a top. Normalize the cross-section, normalized to the standard model value. So 1 is the standard model. And then one can see within the various uncertainties that they're giving, that they are all within the uncertainties around 1. So all the production modes are in good agreement with the standard model prediction, but one can also see that there's still quite large uncertainties. CMS has a similar plot, also with the full run 2 data here. These are again the production modes. One sees again, they are all around 1. And these are now the decay modes. These are these new values that I was mentioning before. So we always calculate, we measure something and then divide it by the standard model prediction. Therefore, we call it the new value. In the gamma gamma mode, ZZ, WW, tau tau, BB bar, and mu mu. And again, we see that they're all located around the value 1. So we have a standard model-like discovery. But, and this is the crucial thing for this talk, this is the second fact, we also know for sure, this is not just something that theorists come up with, this we know for sure, the standard model cannot be the ultimate theory. This is not possible. Gravity is not included. The hierarchy problem. I was told that you heard lectures about the hierarchy problem in the last days. Yeah, so the hierarchy problem is totally not explained in the standard model. This is severe. We don't have unification of the three forces. This is what we would expect in any theory that will be in the end a theory of all nature. Yeah, that the forces are unified. We know that there's dark matter in the universe. Yeah, all attempts to fix it with changing gravity do not work at all, and we need dark matter. The standard model doesn't have a dark matter candidate that works. Very important for the part that I will come to later. We have no idea, or we have some idea, but we have no proof of what's going on, why there is more matter than antimatter in the universe. Yeah, we effectively only see matter. We don't see any antimatter. And this is something that has to be explained. The standard model cannot explain this. There are other things. Neutrino mass are not included. For me, this is more debatable, but still very interesting. We have to go beyond the standard model. And there are also, and I hope to come back to this in the very end, some interesting anomalies that cannot be explained in the standard model. Yeah, but all this leads us to the fact that the Higgs that has been discovered cannot be the standard model Higgs. This is not possible. However, this is cheating a bit, because also the electron that we've observed cannot be the standard model electron in the same sense. But the Higgs is much heavier, and the real question that we want to ask is, and that people are trying to answer at the LHC, does the BSM physics that must exist have any relevant impact on the Higgs? And if so, which model? And the answer to these questions can be given in two different ways. One can look for the changed properties of the, I call it here H125 in order not to say standard model Higgs. It is not the standard model Higgs, it's the Higgs boson with a mass of roughly 125 GeV. One can look for the properties and look for deviations from the standard model prediction. And we have to check for additional Higgs bosons. Everything, nearly all the models that we have predict additional Higgs bosons. And this may surprise you. One has to do these searches, of course, at high masses, above 125 GeV, but equally below. And I'll come back to this later. Yeah? There's a good chance that there are more Higgs bosons also hidden at lower masses that are just have so small couplings that we haven't seen them yet. And I have here a list of the crucial questions that we want to answer. Let's quickly go through them. Yeah. Question 1. What are the couplings of the particle to the other known elementary particles? Yeah. Is the coupling to each particle proportional, really fully proportional to that particle's mass as required by the broad angular Higgs mechanism? Yeah. So we have to test these mass relations. What is the mass, the total width, the spin, and the CP properties of this particle? Yeah. We also want more CP violation for, especially to explain the baryon symmetry in the universe, to explain matter over antimatter. We need more CP. Maybe there's more CP violation in the Higgs sector. We have to measure this. What is the value of the self-coupling of this particle? Yeah, again, is it consistent with the prediction that came in the first slides that I've shown to you today? Is this particle a fundamental particle as in the standard model? Or is it part of a larger structure, modeled with additional scalars? Or it might be a composite state. I understand this was also part of the lectures you heard over the last days. This was discussed in more depth. Yeah, composite states. Oops, I will not go into composite states, but will more go into the singlets and doublets, etc. Yeah. Finally, does this particle couple to new particles with no other couplings to the standard model? And this is, for example, very prominent in the context of dark matter. There are many theories that predict dark matter that only couples to the Higgs and not to the rest of the standard model. And then one can look for this kind of dark matter or exotic particles also. Yeah, there are many. There are also radions or extra-dimensional models predict this kind of couplings. And Atlas and CMS are actively searching for these kind of couplings. Good. Maybe I do this, but before I will go to the concrete model, we take a short break of a few minutes. It's already 1 hour, if I see this correctly. Well, I understand you know at least some BSM models because you were hearing lectures about these in the last days. But as I was saying before, composite models I will not touch, but there's a plethora. There are many, many models that predict BSM Higgs bosons, and I list a few of them here. You can add an additional singlet to the model. Just add a singlet, and as I will show to you, this has some nice features, and I will show you some results for this kind of BSM physics at the LHC. We just add one more singlet, and there's a very good motivation to look at this kind of models. Equally nicely motivated are so-called 2x doublet models, where we have one doublet in the standard model, you add a second doublet. And I can assure you, if you do this, if you work for 10, 15 years with this kind of models, two doublets look completely natural. They look as natural as one doublet as in the standard model. Yeah, so this is really something, a supernatural extension of the standard model. You can combine these two. You can add a doublet and a singlet. And then it depends on the symmetries that you impose. There are many models floating around called N2HDM, S2HDM, 2HDMS, etc. Always two doublets plus a singlet. Nicely, one can also go to supersymmetric models. I will not go into details here today. There's just no time, but there's very good motivation. For example, concerning the hierarchy problem is completely cured by going to supersymmetry. One has here two Higgs doublets. Yeah, so the MSSM is a kind of supersymmetric version of the 2Higgs doublet model. You can also add singlets. Then we go to the N-MSSM. We can more singlets, the model called new SSM. You can also add triplets. This is then the so-called Georgi-Mahacek model. Also, there are many, many models out there, and all have their good motivation, and they should all be analyzed. And the experimental collaborations are looking, in fact, for all these different types of Higgs bosons that are predicted by these models. Yeah, good. And I think this may be the last but one slide before the break. If you construct a new model, if you want to do this because you think that a model has nice properties, you have to make sure a few things. First of all, of course, the model must contain a Higgs at 125 GeV. If not, it's clearly incompatible with the observations. And the properties of the other Higgs bosons that the model produces, the masses, the couplings, etc., they have to be such that they're in agreement with the present bounds. There are many searches from the LHC, from previous colliders. There was a proton-antiproton collider at Fermilab in the United States called Tevatron, which was switched off in the year 2000. I remember. No, 2000 was that. 2010 it was switched off. Sorry. Yeah, they are bounds on this. Before the LHC, there was an E+- collider in the same tunnel called LEP, also produced many bounds. They all have to be taken into account. Finally, there's a very important rule that will play a role in nearly everything that I will say that comes from the structure of these models. This is what they predict automatically. Every model that is an extension by doublets and or singlets fulfills this. You look at the coupling of the Higgs boson in the standard model to gauge bosons and you square it. Now you go to your BSM model and you look at all the Higgs bosons that you have, all the neutral Higgs bosons, with the couplings to gauge bosons, and you square them and you make the sum. And then this sum must be equal to this one here. Yeah, this comes out automatically. And this is a very profound prediction that tells us a lot about the BSM searches. We know that from the measurements that the Higgs at 125 has couplings similar to the standard model. So the sum rule is nearly saturated. There's not much room left that we can give to the other Higgs bosons. And this is very important for all these searches that are currently performed. Yeah, but these two or these three things have to be taken into account. And yes, this will be the next part when we take a short break, 2-3 minutes or so, and then we continue here. And I can again only encourage you, if you have some questions here, please go ahead with them. Yeah. Yes. Good. Let's continue now with a concrete realization of BSM Higgs sectors. And I'll have one in more detail, and then I have two more where I'll be very quick, and then we come to the real physics. So just to know how it works with the physics and with the modifications with respect to the standard model, I choose the simplest model possible. And this is the singlet extension of the standard model. So we take a doublet, as in the standard model, and then we add one singlet. And you can see we also add a vacuum expectation value here. And then this is also expanded around the VEF, and we have, say, this new particle rho S. It's a simple extension of the Higgs sector. And this is actually analyzed also for the LHC nowadays. In the Lagrangian, we have here our normal covariant derivative with the Higgs, and then this here has only the normal derivative. It doesn't have couplings to gauge bosons. It's a singlet. Yeah, it doesn't couple to gauge bosons. And then we have here the potential that mixes these, or that combines the two Higgs fields that we have. And well, one can either impose or not impose the division Z2 symmetry. It's not relevant here. We find in the potential one mass squared term for the phi dagger phi, one for the S squared. And then we have here this mass matrix for the two states. And if one, well, then one can expand it and one finds this combination, these couplings here, the lambda 1, lambda 2, lambda 3 as prefactors for these terms here. So this is the full Lagrangian, and in the original basis, we have the two vacuum expectation values as parameters and lambda 1, lambda 2, lambda 3. Before, we had only one VEF and one lambda, and now adding the additional singlet gives us two additional lambdas and one additional VEF. Good. This is, of course, not the end of the story. We have to ensure that the potential is bounded from below. Before, we required that the lambda is positive. Now, with the several lambdas, it's a bit more complicated. One can work this out. Lambda 1, lambda 2 must be positive, and lambda 3 is given by this relation here. If we go to this unitary gauge, where all the additional degrees of freedom are absorbed into the gauge boson masses, we find that here is the 0, and then we have the V plus the rho, whereas here we have the Vs plus the rho S. So we expand around the minimum, we plug in the VEFs, etc., and then we find that these states, the rho and the S, they have a 2x2 mass matrix. We have diagonal entries, but also we have off-diagonal entries. Yeah, so the rho and the rho S, the two states, they mix with each other, proportional here to the two vacuum expectation values. V times Vs is always in the off-diagonal entry, which means we have to diagonalize this matrix and rotate these two states to get to the two eigenstates. Yeah, this is what's normally done. You've learned either in high school or in the first year university how to diagonalize a 2x2 matrix. It's done via this kind of rotation matrix. Cosine, mixing angle, minus sine, sine, cosine. These are the original states, and then out come our two states with the diagonal mass matrix. So you plug all this in, you get out the two mass eigenvalues given by the combination of lambda 1, V, lambda 2, Vs, etc. Yeah, you can work all this out. And then you have to make sure that one of these two, that you choose your parameters or in a way that one of them turns out to be 125. Yeah, so this is one restriction that you have on the free parameters of the model. And the other one can either be lighter or heavier. Yeah, so by definition, the little h is always the lighter one, the capital H is the heavier one, minus plus here. But you can set either m small h or m capital H to 125. You can calculate the mixing angle. It's also given by all these. And then we arrive at what we call the so-called physical basis, meaning the mass of the two Higgs bosons, the mixing angle that diagonalizes the sector, the VEF, and then a quantity that has shown to be useful in all these calculations, always the ratio of the two VEFs. Yeah, it's just a practical quantity. And we call this tangent beta. This is the second mixing angle here. Tangent beta is given by the ratio of the two vacuum expectation values. We started out with 5 parameters. We're still with 5 parameters, so everything is fine. And the V, this one here must be the V in the standard model, about 246 GeV. Must be like this. So now, then one can express the original parameters in terms of the new parameters, you can transform from one base into the other. This is all easily possible. And it is important to keep in mind that only the standard model doublet couples to standard model particles. So only the rho is the part of the Higgs sector that couples to the standard model particles. The rho s doesn't couple. Yeah, we introduced in a way that it only appears in the Higgs potential, but not with couplings to fermions or gauge bosons. And this means that this little h has a component cosine alpha times rho, whereas the capital H has a component sine alpha times rho. And this means that the coupling of our mixed state, our BSM Higgs boson that we have here, to the standard model is given by the standard model coupling, either with the factor cosine alpha or sine alpha. Must be like this. There's no other way around. What we take from the one, what we give to our new Higgs boson, our second Higgs boson, must come from the first. Yeah, you can't make everything equally large or so. Yeah, this is not possible. So we have this very simple modification factors, cosine alpha or sine alpha. And we can go to the so-called standard model limit in two ways. As I said, we have to ensure that either the light Higgs or the heavy Higgs is at 125, and then we reach the standard model limit either by alpha going to 0, cosine alpha to 1, then all the couplings of the light Higgs become standard model-like, and the heavy Higgs decouples completely from the standard model particles. It interacts only in the Higgs sector, but not with gauge bosons or fermions. Or the other way around, if we choose M capital H 125, we take alpha to pi over 2, then sine alpha goes to 1, and the same holds. This one here has standard model-like coupling, and this one here decouples effectively from all standard model particles. Now, the sum rule that I talked to you before, the very crucial sum rule, and this is the easiest example because you know the sum rule, boils down to cosine squared alpha plus sine squared alpha. And we know that this is 1. Yeah, so we get out this from the sum rule that you learned in high school or so. Now we have the decay width. So the strength of decay of the light Higgs to standard model particles is given by the decay of the standard model Higgs, of course, using the same mass value here, times cosine alpha squared, because cosine alpha, as I was saying here, is the one that multiplies the coupling. The coupling enters squared into the decay width, and then you get this prefactor cosine squared alpha, or for the capital H, sine squared alpha. Well, and there's one thing that is different, and this will play a crucial role for what I will tell you in a moment. Of course, it is possible that this capital H is larger than 2 times the light one. Let's say this is 125, and then this is larger than 250. Then this decay is kinematically allowed and must be taken into account. And we can even look for it and profit from it. And this is what I will show to you later. And if you look at this more detail, you can calculate this decay width, has this phase space factor, and then these couplings here. You can calculate it, but if you calculate then the total width of this heavy Higgs boson, which is given by sine squared alpha times the standard model width, plus this one here. Yeah, so this always comes on top, whereas for the light Higgs, we don't have an additional factor. We only have this suppression factor of cosine squared. And then you can calculate the branching ratio. And the nice thing is the branching ratio for this one here is like in the standard model. And here we have and for the heavy Higgs one, we can get, so where did I write this? No, we can have the additional decay of this one. So the branching, the total width changes, yeah. And if you work everything out, you will see that this is given now, the branching is given by sine squared alpha times this ratio, and we have this additional branching ratio, so that the sum again sums up to 1. This is how one can calculate it. Good. This was the simplest model very, very briefly, I'll touch upon models with 2x doublets and 2x doublets and a singlet, just to give you the most basic idea of it. Yeah. If you have 2 doublets, again, the Higgs potential becomes more complicated. You have more possibilities to combine these 2 Higgs fields. Therefore, you have more lambdas in the game. And now we add 4 degrees of freedom. In the standard model, we have 1 Higgs boson. We add 4 degrees of freedom. This means we must have 5 physical Higgs bosons in the spectrum. Yeah, there's no other way around. They don't disappear. They must manifest itself as Higgs bosons. And in fact, if one works this out, one finds that in this model, one has 2 CP even Higgs bosons, a light and a heavy one, 1 CP odd Higgs boson, and a pair of charged Higgs bosons. This may surprise you at first sight, the Higgs bosons with an electric charge, but if you think about it a bit more, there's nothing strange about it. Just why shouldn't it have an electric charge? In the standard model, let's say this is the standard model doublet, this CP odd component and then in these 2 components with the charged one, they go away to give mass to the Z and to the W bosons. But here, this charged component remains and it must manifest itself as a pair of charged Higgs bosons. So the basis that we have here is, again, we have 2 mixing angles, alpha and beta. This is cosine beta minus alpha is a nice quantity in this game, tangent beta. We have the VEF, we have the mass of the Higgs bosons, and we have 1 parameter from the potential that remains, M12 squared, given here, that mixes the 2 Higgs fields. Yeah, and I'll skip, well, yeah, I'll skip this. You can look up the details if you're interested. You have modification factors, the sum rules, everything works out nicely. The only model that I want to briefly introduce is the model with an additional singlet. It's either the N2HDM or the S2HDM. You can see here, 1 doublet, 2nd doublet, plus a singlet. And I'll tell you later why this is interesting. Again, the Higgs potential becomes even more complicated. There are more possibilities to combine the various Higgs fields. You can apply several symmetries to reduce the number of these parameters, these new parameters. Important thing is now with 2 doublets, we had 5 physical Higgs bosons, adding 1 degree of freedom. Now we have 6 physical Higgs bosons. Yeah, the counting is really trivial. And in this case, it's a CP even one that we add. So we have here 3 CP even Higgs bosons, 1 CP odd, and a pair of charged. And in this way, you can extend the Higgs sector as much as you like. You should always have a good motivation to do this. And I'll talk about motivations in a moment. But this is how one can do it. And yeah, maybe the last thing that I will say now, here, this will be crucial at the very last part of the talk. We have 3 CP even states. They must rotate into the mass eigenbasis. And this is now not given by a 2x2 matrix, but by a 3x3 matrix. And this will become relevant in a moment. Yeah, governed by 3 mixing angles, alpha 1, alpha 2, alpha 3. But if you understand the Higgs singlet extension, you also understand all the other extensions. Yeah, the construction is always the same, the features are the same, etc. So it's really, if you get the first simple model, you get all the rest nearly for free. Good. I skip this and I come to BSM Higgs physics at the LHC. By the way, this little drawing was done by a PhD student of ours, Katharina, who is doing her PhD in Hamburg. She is not only an extremely good physicist, she is also this, she knows how to draw things. I have a few more drawings of her, but this is, I like particularly. This is BSM Higgs sector. Yeah. Good. Now, motivation. Well, I told you, why do we look, or what do we do at the LHC? What do we want to answer? Which quest do we want to answer with our BSM Higgs sector? And as I said, I will go for one selected topic, which is one of the hottest topics these days in BSM Higgs physics, or in Higgs physics in general at the LHC, which is di-Higgs and triple Higgs couplings. Okay, and I will motivate why this is important, and then I will show you what is being done at the LHC and etc. Yeah? So, the Higgs potential. what do we know? We hardly know anything. Yeah, we know, well, this is a very simplified form in a simple Higgs sector. Yeah, this is the form that we've seen before. And we know this distance. This is the VEF, 246 GeV. And the mass tells us how the curvature is around here. Yeah, like the Higgs potential, this is the mass determines the curvature. We don't know how it behaves here or how it behaves here on this side. We don't know anything. We don't know how it continues, whatever. In order to know more about the Higgs potential, is very simple. We have to measure more of the Higgs self-interaction. If we get a handle on triple or quartic Higgs couplings, we know how the Higgs sector really behaves, how it continues here and here. I come back to this in a moment. But the real physics motivation is one of the big questions that I posed before. Why is there more matter than antimatter in the universe? We effectively only see matter. And there's one mechanism, which I will not explain because there's no time for it. It would be in another hour or so. A mechanism that can take place in the early universe. It's called electroweak baryogenesis. Take it as a word. And this can take place at roughly when the universe was 10 to the minus 10 seconds old. And there are several things that this mechanism requires to create the matter-antimatter asymmetry. And one of the conditions, these were given by a Russian physicist called Sakharov, very famous, and therefore these three conditions are called the three Sakharov conditions to explain the asymmetry between matter and antimatter in the early universe. And the third condition tells us that we have to be in an out of equilibrium condition, which corresponds, and I'll show you what this means, to a first order electric phase transition, to an abrupt phase transition in the early universe. I show this to you on the next slide. And it has been shown that this is not possible in the standard model. It would have been possible in the standard model with the Higgs mass below 75 GeV, but we know the Higgs mass is 125, and therefore it's not possible in the standard model. So we need a BSM Higgs sector to explain the matter-antimatter asymmetry. We want to learn about the shape of the Higgs potential that will tell us how this first order electric phase transition may have taken place. And this, first of all, requires, it's practically a hard bound, that there must be new Higgs bosons below 800 to 1000 GeV. Yeah, so this is, if this electric baryogenesis takes place, then there must be an extended Higgs sector with Higgs masses not heavier than this, which is a very good news because we can look for them. We can try to find them at the LHC. Yeah, and there are several interesting phenomena that are related. We can, what I call here, look for resonant di-Higgs production, meaning we produce the heavy Higgs, what I was showing to you, that then decays to two light Higgs bosons. This is the one decay, the additional decay that the heavy Higgs and the Higgs singlet extension can have. Yeah, so this can happen, and people are looking for this. Furthermore, there is not only one triple Higgs coupling, as we normally have between the 3 times the 125, but there are now also BSM triple Higgs couplings involving the heavy Higgs boson, and we have to look for them, and we have to try to measure them. We not only want to measure one triple Higgs coupling, we want to measure BSM triple Higgs couplings. And all this is ongoing research, really. These days, I would say, or the most important results on new Higgs measurements over the last years, I think they're mostly done in this area here. Di-Higgs production, triple Higgs couplings, etc. Yeah? There are many people work on this right now. Yes, and I wanted to show you what I mean with this first order electric phase transition. So let's look at the right side first. This is the Higgs potential shortly after the Big Bang. And the temperature is, now we live at temperature 0, but those days we were living with a finite temperature. And of course, in the beginning, this cools down, and then eventually goes to 0. So this is the highest temperature. And if we take the standard model prediction, what happens is that with lowering the temperature, the shape of the Higgs potential changes a minimum is formed here, and the ball always indicates where the minimum is, where we live, where the universe lives at that moment. And then it goes to the minimum and stays at the minimum. Now we are here. Yeah, this is the VEF, and we have this smooth transition from the origin to here. This is either a second order phase transition or what's called a crossover, even weaker than second order. And this is what happens within the standard model. Now, in order to have these baryogenesis working, we need this out of equilibrium, meaning we need a first order electric phase transition. And this can happen in a BSM Higgs sector, which is shown on the left here. We start out with the same potential. Now the temperature goes down, and then the second minimum starts to form here. Second minimum, yeah, you see here. Now we have a second minimum, still higher. Then at the temperature Tc, they have the same depth. And at a slightly lower temperature, this one here is below. And then a tunneling process takes place. It's a quantum tunneling process. And abruptly, we move from here to here. This is the out of equilibrium moment. As I said, happens around 10 to the minus 10 seconds after the Big Bang. And it has been calculated that this indeed gives the first order electric phase transition and can then realize electric baryogenesis with some other ingredients that I will not discuss today. But we need a BSM Higgs sector. And how can we visualize this? This is at 10 to the minus 10 seconds. And now at some point, for example, here in the center of this bubble, the tunneling to the correct vacuum took place. And since this is an energetically favored state, these bubbles expand nearly with the speed of light. And inside, we are at our VEF non-equal to 0, whereas outside here, we are still at the VEF equal to 0. But in the end, these bubbles will fill out the whole universe. And yeah, this is now the universe where we live in, where this V is about 246 GeV. This is the picture one should have. And the question is, in which BSM Higgs sector can this happen? And what are the implications for the triple Higgs couplings that so far we've looked at only very briefly? And we'll come to this. And I write this here. There's a nice bonus, but I will also not go into details. The collisions of these bubbles, they can cause gravitational waves that may be detectable with future space-based gravitational wave antennas. There's one project actually approved called LISA. Launch date is in 10 years or so. They will send 3 satellites in space. They are like the one on Earth, LIGO, Virgo, Kagra, etc., but much, much bigger. So they have 2.5 million kilometers distance between the satellites. They send lasers back and forth, and then they can measure this kind of gravitational waves, depending on how strong this was. So but this is a BSM Higgs sector here. Oh, just a moment. I have to. Just a moment. Oops. Good. Yes, let's continue. Good, gravitational waves, but we will not discuss this further here today. Now, I showed you this very simple Higgs potential, yeah, where we know only what happens where we are sitting now in the electric vacuum. But once you go to more complicated Higgs sectors, things can become much more complicated. And in the end, we will have to measure everything. This is another drawing of Katharina here, where we are living here. And then there can be additional deeper minima. There's an absolute minimum. There can be deformations over the whole field space. It can become very, very complicated, yeah? And we only know this little bit here. We don't know anything about these others, yeah? This all has to be explored in the end. And I will show you how to go some steps in the direction to explore these. Well, good. And as I said, the first step to know something about BSM Higgs sectors is the measurement of trilinear Higgs couplings, because the trilinear Higgs coupling, the coefficient that is in front of 3 Higgs fields, of course, tells us about the shape of the potential. And this is a very famous plot that has been done in 2019, which tells us what to expect here. This trilinear Higgs coupling given here, divided by the standard model value called kappa lambda or kappa 3, this is the same. The precision that we expect at the high luminosity LHC is about 50%. So very bad, well, it's something, but not much. Right now there are updates being done and hopefully this will become better, but this is the official number so far, 50%. And then there are future collider searches, either at the plus and minus colliders, can be circular or linear. And once you have an energy that allows you to produce 2 light Higgs bosons at once, then you can get to relatively high precisions. This is shown here or so, yeah. Then you can get to very high precisions at the level of 10%. If you don't have enough energy, then all your measurements will be inherently much worse. However, this plot here, it's really the most famous plot in this context, based on the high luminosity LHC assumptions here, has 2 drawbacks. First of all, it always assumes that the coefficient of the triple Higgs coupling has the value as in the standard model. And the second one, no BSM triple Higgs couplings like this one here are taken into account. Yeah, therefore, one has to look out for this. Good. Now, how does it look like at the LHC? The Higgs reduction. Let's forget about this diagram for the moment. If we want to produce 2 Higgs bosons at the LHC, there are 2 diagrams possible that contribute. We can here have, well, we start out with 2 gluons. They form a top triangle, and we get out 1 Higgs at 125 GeV that then decays to 2 Higgses at 125 GeV. So this one is off shell, but here's where the triple Higgs coupling enters. Yeah? This is the process we can search for, that is actively searched for, and that we are after. The other process that competes with it, or the other diagram that competes, is where we have a top box, and then the Higgs is radiated twice from the box. And so we get 2 Higgses, but without any knowledge about the triple Higgs coupling. And the problem is that there's a negative sign here that interfere destructively, and therefore the access to the triple Higgs coupling is kind of diminished. Then there is this cross-section prediction here. The cross-section for di-Higgs as a function of the value of the triple Higgs coupling. 1 is the standard model value. So we are here, this is the prediction. And then if we make the coupling larger, the destructive interference grows and the cross-section goes down. And this means that it will be very difficult to measure this triple Higgs coupling if it doesn't have the standard model value, if the value is 2 or so and not 1. Yeah, we go down here in the cross-section and all these measurements become much more complicated. And a lot of work is devoted to this kind of scenarios these days. Now we also want to do this in BSM Higgs physics. And there I will just tell you, there's one more ingredient that one can take into account. These are again these 2 diagrams that I've shown to you before. And it is possible to insert here the BSM value of the triple Higgs coupling. Not only the tree level value like the standard model value, but we can have BSM value here. And this can drastically modify the Higgs production. And I'll show this to you in a moment. Yeah, this can all be done in a consistent way and gives us hints and clues how to see if BSM effects in the Higgs production and to learn about BSM effects in triple Higgs couplings. But there's another effect, and this may be even more important, and this is the 3rd diagram. This is the diagram we are really after, where we produce a heavy Higgs boson, which then decays to 2 light Higgs bosons. And this is, first of all, we have a BSM particle here, which is great. Yeah, we haven't seen any BSM, so we would have a BSM Higgs boson here. And then we even have a BSM triple Higgs coupling. So we would learn more about the Higgs factor by measuring this coupling. This would be really great. And a little, not a caveat, but a little sad truth here. As I was saying, Atlas and CMS, they're looking for the Higgs production. They devote a lot of person power right now to find the signature of 2 Higgs bosons. And then there are 2 types of searches. One search is standard model-like, where they take these two diagrams into account, but this one is neglected completely. You can do this. The other possibility, and this is what is not done very well so far, they look for this kind of effect. But by doing so, they neglect these two diagrams. Yeah, and they only look for this diagram. However, these two diagrams, they're always there. Yeah, we always have this 125 boson, and this box is also always there. And the experimental analysis, I'll show this to you in a moment, they're not really sensitive to what they should be sensitive to. Yeah, this is a drawback of current LHC BSM Higgs physics. And I have some examples here, which I will go through quickly. Some are given in the Higgs singlet extension, and some are given in the 2X doublet model. Yeah, these are the two models that we were using so far to look at this kind of effects. Now, this is the last really important concept that I'll introduce to you today. And this is the so-called MHH distribution. Now, what is this? Imagine we produce two Higgs bosons, then we can reconstruct their 4 momenta. Yeah, this is the idea that you see something in the detector and you can reconstruct the two 4 vectors. You can add them up and you square this. And this is the so-called invariant mass of the di-Higgs system, MHH. Yeah, the invariant mass, or the kind of the energy that is contained in the di-Higgs pair that you're looking for. And all these searches that we're looking for are based on this kind of predictions, or searches involving this MHH distribution. Then there's not a total cross-section, this is a differential cross-section with respect to the di-Higgs invariant di-Higgs mass. It starts, of course, at 250 GeV, 2 times the Higgs mass. It rises and then goes down to very low values again. Now the red line, the black line is the standard model prediction. Now, if you look very closely, it starts here, has a maximum, and then goes down. This is the standard model prediction. On the other hand, we have BSM effects. And I told you there are 2 types of BSM effects that must be taken into account. And we try to convince our experimental colleagues to take them into account as it's being done here. First of all, the triple Higgs coupling can have a different value, which is caused, for example, by higher order corrections to the triple Higgs coupling. And we have the BSM effects. And if we take both into account, I'll just give you the final answer here. Said in the standard model, we have this MHH distribution. Now, for one parameter point in the 2HTM, we have this distribution. It starts out very high, many orders of magnitude higher, then goes down, then has here this peak structure and goes down again. Now, this effect here comes from the different value that the triple Higgs coupling of 3 light Higgs bosons has in the model. In this case, it has a value of 3.6, where 1 is the standard model value. It's much higher, but totally allowed by all measurements and searches. And this here, where this peak is, or this in reality, it's a dip peak, this is where the heavy Higgs boson is located. Yeah, the mass of the heavy Higgs boson is exactly here. And then this diagram becomes active, and exactly where the heavy Higgs is located in this MHH distribution, you get this peak dip structure, very characteristic, and experimentalists are looking exactly for this to identify resonant di-Higgs production. Or this is what they should be looking for. I will tell you what they're actually looking for. Now, this is, of course, the naive theory view that I presented to you. In the experimental reality, there are 2 effects that have to be taken into account. One is the fact that you not always measure the MHH value correctly. It can be a bit higher, a bit lower or so, yeah, because you have some experimental resolution, meaning that it's smeared with a Gaussian. Every measurement is smeared with a Gaussian. And then this, for example, the red line is now the full result that I've shown to you before. And this is the original one here, it has a peak. And then if you include the smearing, the peak becomes this very broad peak. This is what happens. What our experimental friends are doing is something different. they look only at the diagram with the capital H, then they get out the blue curve, and then they smear it here. So this is what they are looking for. This is not the end. There's another effect. Also, the resolution in MHH in the end is not infinite. You can always get them in bins of something like 50 GV. So in the end, this nice smooth curve with a very prominent peak in the end looks like this one here. So there's a little shoulder remaining, and it's very broad here, and so it looks much, much uglier. Therefore, it's so complicated. Yeah, this is what shows how complicated it is to look for di-Higgses and for BSM effects in the Higgs searches. Good, and I show you just one example. I told you our experimental friends from Atlas and CMS, they only take into account this resonant diagram. They produce, for example, this blue curve. They train their networks and their analysis on this blue kind of curve. And then they tell us what part of parameter space is excluded. You can do this, but we took our parameter point, the parameters are given here, and we take into account all the diagrams that contribute, not only the resonant one. And then what we get out is the red curve. So we are told, we tested this, our codes tell us that yes, the experimental search excludes this parameter point, but based on the blue curve. Reality is the red, and it is clear that anything trained on the blue curve must be erroneous when trying to look for the red curve. Yeah, so the limits that we are getting for this resonant Higgs production right now in the area where we are interested in, they are not reliable. Yeah, and we try to, this is an ongoing topic of research to try to improve them. Good, I'll leave this here and I'll show you some results in the simplest model. In the simplest model, the Higgs singlet extension, where we require now that we live in a parameter space that gives us this first order electric phase transition. Yeah, I told you this is the main motivation to go for BSM Higgs sectors. Now we have in this one, and we can realize this in the Higgs singlet extension. It's possible, even in the simple model. And then we have here the plane of the BSM triple Higgs coupling and the triple Higgs coupling of 3 times the light one divided by the standard model value. And this is a plane that was defined where we always find the first order electric phase transition. Very good. And just to make this clear, this is the mass of the heavy Higgs boson that we have in the model, ranging from 450 to about 675. And I told you, the first order phase transition predicts that the masses must not be too high. This is exactly what we see here. So this idea tells us we should look for those at the LHC. There is a chance that we will see it actually. This is the nice thing. And you can calculate the total cross section. We've done this here in the same plane. Here the color coding tells the total cross section. Red is the standard model. Yeah, so here we find standard model values, and then we find values slightly below and somewhat above. However, as you can see here, this kappa lambda is around 1.45. Yeah? And if we remember this plot here, 1 is standard model. Now we go to higher values, then the cross section must go down a lot. But what we find is that it can be a bit lower, but it can also be higher. How can this be? Because we have 2 BSM effects. We have the BSM effect from this triple Higgs coupling, and we have our heavy Higgs in the game. And the heavy Higgs usually adds to it. And then they can compensate. Here in the red area, they are compensating. And so there are many BSM effects conspiring, in this case, to give you a standard model-like cross-section. And you have to think harder how to identify this at the LHC. And what one can do, we did this and we defined some benchmark points around the plane here. Not go into details, but we look at these distributions, the MHH distributions that I mentioned before, where we introduce the smearing and the spinning to make it experimentally more realistic. And okay, I'll skip the details here for sake of time. But here the red line is the standard model, or the red dashed line is the standard model, sorry. And then we have two benchmark points, P1 and P2. And they show, although the cross-section is only slightly, is somewhat different, but we see still a very prominent peak here. A very prominent peak that can be searched for experimentally. Yeah? If this is our expectation, and we see this here, this would indicate there must be a heavy Higgs boson. And this is the worst case. These are 3 points for which the total cross-section is the same one, effectively the same as in the standard model. But looking at this distribution, comparing red dashed with these, what we call P5, 7, and 8, these different lines here, we see deviations here. Here it's smaller, and here we still have this peak structure. Yeah, so the peak of the heavy Higgs compensates the effect of the difference in the triple Higgs coupling. And in this way, the total cross-section comes out the same, but the differential cross-section still looks different. And we try to convince our experimental friends to look for this, and we try to develop methods to really distinguish this from the standard model expectation. Yeah, but this is the way of physics that is currently going on for BSM Higgs bosons at the LHC. Yeah? This is one of the really hot topics that are currently pursued. It is already 6. I have to give you the summary, and then we'll see whether I tell you anything else. So large router spaces with relatively low masses are allowed and possibly even favored from the requirement of the electric symmetry break, from the requirement of the baryogenesis. If we have a BSM Higgs sector, we find that this kappa lambda, the ratio of the triple Higgs coupling divided by the standard model value, is often different from 1. And in many models, we find that values between 1.5 and 2 are favored. On the other hand, this is one BSM effect. The other BSM effect is that there are the heavy Higgs bosons in the game, where here we have a triple Higgs coupling between 2 light and 1 heavy one. One can get access, experimental access to this kappa lambda and the BSM Higgs coupling via this process. Glue goes to 2 Higgses. And here the MHH distributions are crucial. They are key in this kind of investigation. This is what the experimental physicists are using. Yeah? At low values, I said this briefly, the deviations in kappa lambda are crucial. And then when these two are the same, this MHH is roughly the mass of the heavy Higgs boson, then we get this peak and dip structure from the resonance of the heavy Higgs exchange, where this triple Higgs coupling enters. Yeah? And when we look at this, even in the simplest model, in this one singlet extension, it seems that there is experimental sensitivity in the part of parameter space that is favored by the requirement of the first order electric phase transition, which we need to explain the baryon asymmetry in the universe. So this all kind of adds up, but this is all ongoing investigation. This is where theorists and experimentalists are working on these days. Well, I would have my favorite anomaly, but it's already 6:05, so maybe we stop it here and we can discuss some things that have remained unclear. And if anybody is really interested in this, I can say a few words as well. But I think I talked for 2 hours. This should be sufficient. Thanks a lot.